Okay, good. The recording has started. Hi guys, my name is Bhavya Rai. Again, to introduce myself. Okay, and I am currently a PhD scholar at IIT Madras. Okay, and I research in theoretical computer science. So, in case you missed the introduction last time, I'll be doing weekly problem solving sessions on this NPTEL course of computational complexity. Okay, and if you have any doubts, we can discuss at the end of the class, and or if it is a short doubt, probably we can discuss at the beginning also. Okay, and so the way that I'll operate is that I'll solve a few questions from the previous assignment, and I saw that the assignment is due on 7th August. So we cannot. The first assignment is due on 7th August. So we cannot discuss it yet. Okay, sadly, but the next problem solving session, I'll be discussing assignment 1 also. Okay, and okay, so by the way, I did not give any references. So 2 points. First of all, these contents, okay, the notes that I'll write will be uploaded to a Google Drive. Secondly, the videos that I record here will be uploaded on YouTube also. But of course, I recommend attending the classes so that we have some kind of interaction, so that there is a better takeaway from this course. Okay, and that being said, yeah, resources. So the course uses 2 books, Aurora Barak, okay, and which is Computational Complexity, a Modern Perspective. And I believe there is also another book which is quite famous, which is by Michael Sipser, okay, which is a Theory of Computation, Introduction to Theory of Computation. Okay, good. So yeah, and one extra book that I'd like to recommend, okay, is this book called Nature of Computation. I think there are 2 authors. I'm sorry, I cannot recall the name. Maybe next time I'll give it to you. But this is another really nice book. Okay, this is a slightly philosophical take on theory of computing. Yeah.
So the name of the author is Chris Moore.
Can you say it again?
Chris Moore.
Chris Moore, is
Moore.
it? Okay, Chris Moore. Nice. Thank you. Thank you, Goel. Okay. Uh, yeah. So it's Nature of Computation is by Chris Moore. A wonderful book. You should definitely go through it once. Okay. And now let's begin once again. The last class that I did was directly on problems. I didn't discuss much theory, but from what I can understand is I should be discussing some kind of theory so that you guys get a bit of a recap. That is the kind of feedback that I sort of received from the class that I had that time. So yeah, so this particular question that I can show you here is a question that I could not discuss fully during the previous week. Okay, so I'll discuss this, but I'll have a certain sequence in which I'll discuss. Okay, so I'll skip this one now. I'll come to this. I'll come to this. I'll come to this, and okay, I'll start with this. Okay, so the topic. Okay, what are the topics? Okay, the for this week, that is NP-completeness and polynomial hierarchy. Okay, these are the topics. So so I'll just quickly go over it. So what is P? P is the class of all languages, okay, or problems that can be solved in polynomial time. Okay, by Turing machine, a deterministic Turing machine, to be exact, by a deterministic Turing machine or a deterministic algorithm. Okay, this is equivalent. Okay, and we did some examples last time. For example, check if, one moment, I'll admit this person said, okay, yeah. So for example, checking if graph is a tree, or checking if one vertex can be reached from another vertex, giving algorithms like BFS, DFS. So that is in P. And NP is quite interesting. It is again the class of all languages, okay, or problems that can be solved in polynomial time by a non-deterministic Turing machine. Okay. So, and interestingly, this is the first definition that is possible. Okay, and if you've done a TOC course, you may know that a non-deterministic machine is just one which is able to perform several choices at once. Okay, it can move to several states at once, and if any of the choices, non-deterministic choices, actually leads to an accepting path, then the machine is said to accept. Okay, and you may have seen it in the lectures. For example, if this is the starting configuration of a Turing machine and it makes several choices, let's say it flips a coin, says 0 1, and then it goes to two different states possible, and then another coin flip which goes to two other different states, and then it makes these different choices. Of course, there may be more than two states, but there is a argument you can make that even if you um, do a binary tree, then this is enough. Okay, and finally, if one of the states is an accepting state, then the machine is accepting. Okay, so this is what a non-deterministic Turing machine is. This is how it goes, or a non-deterministic algorithm it is. Yes, okay, so there are several branches of computation. For example, this is one branch, this is another branch. Okay, and this is another branch. Okay, and several branches are there, and so this branch is an accepting path, and this is a rejecting path, say, and this is again rejecting, and so on. So can you tell me how many such branches are possible? How many such paths are possible, computation paths are possible, if the uh, if this is of length polynomial on it, say some n to the k. Let's say the number of coin tosses I can make is some n to the k, where n is the input size. How many such branches are possible? How many such computation paths are possible? 2 to the power of n power k. Now, why is that? Because good, Suraj. Why is that? Because if you look at a binary tree, okay, of a certain depth, this is a full and balanced binary tree, as we call it in data structures, right? So, and what is the depth of this binary tree? Right, the depth is the number of edges in the number of levels of looking at the edges. Okay, and how many branches are possible? Let's see. This is one branch. This is another branch, two, and then three, then four, then five, then six, then seven, then eight. There are 8 branches possible, and number of branches is equal to 2 to the 3, which is 8. So you can try to prove this offline, okay? But yeah, this is the idea, that you have so many branches, and so if you try to explore them one by one, how much time will it take? It will take exponential time. So it is not clear whether, now if you, that is, if you want to make this thing deterministic and you want to visit each branch one by one, that is, you test the first branch and then you test the second branch, okay, and then you test the third branch, okay, and then you make a deterministic machine out of it. Deterministic meaning there is no non-determinism, so each state will lead, you know what the next state will be. So this is what it will look like. And since there are 2 to the n to the k many branches, you will need at least 2 to the n to the k times some n to the k, because this is of size n to the k. So you will take exponential time to visit each branch, okay. So it is, so it looks like NP, okay, those languages which can be solved by such kind of computation is more powerful than this, right? Because if you want to make it into a deterministic computation, you are losing time. So the question about whether P is equal to NP is a question. So one thing you already know probably is that P is contained in NP. Why? Because P is simply just a single branch in the non-deterministic machine. Okay, polynomial length branch in a non-deterministic machine, polynomial length computation, and this is fine. But whether any problem in NP can be changed into a problem in P, that is without this exponential blow up, you want it to run in P time only, polynomial time only, that is not clear. That is what we want to see, okay. And finally, and this leads us to the question of NP is equal to P is equal to NP. That is a huge question, $1 million question, right? And so now this brings us to another definition of NP, which is as follows. If I already give you what branch to explore, okay, this sequence of zeros and ones, which will lead to an accept state, then you can easily check, right, whether the machine will accept or not. Now this sounds kind of vague, but this is this will lead to the definition. That is, what is NP? In other words, is the class of languages, right, which have polynomial time verifiers given verifier, let's say Turing machine, given polynomial size certificate. Now let's say, okay, let's say this is my non-deterministic Turing machine, okay, and I tell you to check whether, using a deterministic machine, whether this non-deterministic Turing machine accepts or not, okay. And what I'm going to do is, okay, I'm going to supply you with a branch, and you're just going to explore that branch, okay. Instead of tossing the coins 0 1s on the way, I'll just give you the sequence, whether heads or tails, whatever. You'll take a 0 first, then you'll take a 1, then you'll take a 0, and so on, okay. Question is, will that branch lead to an accept or not? Well, if the non-deterministic Turing machine is supposed to accept, okay, if the non-deterministic Turing machine is supposed to accept, then it will have at least one branch which will accept. And suppose I give you that exact branch, then in deterministic time, okay, in deterministic polynomial time, you'll be able to tell whether the language belongs, and given this branch and given an input, you can tell whether that input belongs to the language or not, whether my machine will accept, my non-deterministic machine will accept or not, right? And this branch is exactly my certificate. Getting it? So from this definition, we can move on to this definition. There is a polynomial time verifier Turing machine. What does the verifier Turing machine do? It takes in the branch, okay, and then just simulates the non-deterministic machine on it. It does not actually toss the coins. The coins are already given to you, whether to move from 0 or 1, or 1 to, from, which state to move on, 0 or 1 at each point of time. And this branch that I give you is called a certificate. Because why is it called a certificate? Because if your machine is to accept on that input, my machine will definitely say will have a branch which will lead to an accept. So for that input, this branch, for that input, there is an accepting path, and this path is exactly my certificate. Okay, so I think that is clear now, right? So let me know if there are any questions about this. Is it all clear?
Yes.
Okay, good. Remaining people, um, Sagar, Rosalind, Goel said, okay, cannot.
But this verification things seems quite easy. So, are
Right,
there problems wherein the verification itself becomes pretty difficult? Because in P class we are actually solving a problem, and wherein for the MP we are only verifying the
right,
solution in real time, and moreover this P is a subset of the MP.
right. So, okay, good question. So, what Goel asked is that, so the verification part is easy now, because what do we mean by easy? We mean that it can be done in polynomial time. Okay, and so what Goel asked is are there languages, are there classes where verification may not be easy? There are languages where even verifying them are difficult. Okay, and I don't want to spoil the course for you, but yeah, such kind of languages do exist actually. Okay, and the this week's course on polynomial hierarchy is actually kind of based on that only. So that, are there languages more harder than NP? Okay, that is what the question. And yes, there are definitely languages which are difficult to verify, which can be proved to be more difficult to verify. Okay, and and so Goel, I'll just point you to week three's content, which is something called the time hierarchy theorem. Okay, and this is in week three content, which is already released, so you can check it out once. And specifically on non-deterministic time hierarchy theorem, this will answer your question. Okay, and your answer lies in something called NEXP, a class called NEXP. This is definitely harder than NP, and therefore more difficult to verify also. It will take exponential time to verify. Okay.
Okay, I'll check it out.
Okay.
Thanks.
Okay, great then. I think that is fine. Is there any message? Okay. Okay. So here's the question. Okay, based on that, show that the following languages are in NP. Okay. First, you have Hamiltonian path. G is a graph which is containing a Hamiltonian path. Now, what is a Hamiltonian path? Okay, a Hamiltonian. Okay, does anyone know what a Hamiltonian path is already?
So, to traverse every vertex exactly once in a graph.
Yeah, exactly. Every vertex have exactly one. And what about the edges? Are we allowed to repeat the edges?
Yes, edges can be repeated.
Are we allowed to repeat the edges? Okay, edge repeating does not make sense. Are we allowed to repeat the vertices? Sorry.
No. In case of the Hamiltonian, every vertex, to traverse all the vertices of the given graph, wherein every vertex would be traversed only once.
Okay, good. Every vertex is traversed only once, exactly. So Hamiltonian path. Okay, please don't mind my bad handwriting. Hamiltonian path. Okay, is a path that traverses every vertex exactly once. Okay, every vertex exactly once, and at the same time plus visits all vertices. For example, um, A, B, C, D, E. Yeah, can you tell me a Hamiltonian path here? any Hamiltonian path in this graph?
So it could be A, E, D, B, C.
Okay. A, E, D, B, C.
C.
All the vertices are visited,
Yeah.
and all of them are visited exactly once. And Suraj is saying D, E, A, B, C. Okay. D, E, A, B, C. That is good. Yeah. Good. And say okay. I'm not able to come up with counter example. Does this have a Hamiltonian path? Yeah. As long as there is a cycle which visits all of them, there will always be a Hamiltonian path. Yeah. So avoid large cycles. Yeah. I think this is. So does this have a Hamiltonian path? Right. Rosalind? Yeah. Good. Suraj. This will not have a Hamiltonian path. Why? Because if I start from A, let's say, then I visit G, and I need to take care of this guy. Okay. And but to do that, I need to repeat D, which is a problem. And if I start from G, then I can either choose to visit this side or choose to visit this side, and either way I need to repeat D again. Okay, so this is an example of a graph that does not have a Hamiltonian path. What is my language? It is a set of all graphs. You can imagine, let's say G is given as an adjacency matrix. Okay, some kind of binary encoding, where G is a graph containing a Hamiltonian path. Okay, so the set of all G containing Hamiltonian path. If I need to have a Turing machine which decides whether it belongs to my language ham path or not, then the equivalent problem can be stated as, given a G, is G containing a Hamiltonian path or not? Is there a Hamiltonian path in G or not? Okay, and is this problem in NP? Can you tell me?
Yes, this is an NP because if you give me an assignment of the vertices, I can verify it in the polynomial time.
Assignment of vertices. You okay? Give the sequence of vertices. You mean, right?
Yes.
Right. Good. Yeah. I mean, whatever you just showed me, okay, about pointing what is the like, for example, Goel or Suraj showed exactly what the Hamiltonian path is, right? And that is exactly what our verification will be. That is exactly the certificate. What is the certificate? Certificate. Okay, let's say for a yes instance, okay, yes, there is a Hamiltonian path. If you say, then what is the certificate? The certificate is simply the Hamiltonian path itself. Example, like D, E, A, B, C, or what did you say? A, E, D, B, C, right? So this is the certificate itself. And the size of the graph is, and this, what is the length of this? The length of this path will obviously be n, right? The length of this path will be n, and maybe the labelings will be something like log n, but it can be represented in polynomial space. It can be represented in polynomial to the size of the graph. Okay, and the size of the graph is some n square because it's represented as an adjacency matrix. The size of graph is some n square. It's shown as an adjacency matrix of n vertices. So It will take some n times n, which is n square, right? So it will take polynomial in n square, the input. So therefore, and what if it's a no? Okay, right? What if it's a no? Like you guys, um, Rosalind and Suraj had said it was no, right? And how did they do it? I mean, you could intuitively do it, but for a machine to do it, you just go across all possible, you know, Hamiltonian paths that you may try to create. Okay, and but you realize that there are no Hamiltonian paths, and therefore there are no certificates also, right? So no, then of course you cannot find a certificate. Because if your certificate is a Hamiltonian path itself, and if the answer is no, of course you cannot find a Hamiltonian path, right? So okay, good. So Hamiltonian path is in NP. Okay. Okay, another simple one. Okay, this time we'll be quicker about it. Subset sum. Okay, subset sum is a pair S comma T, where S is a set of positive integers. Okay, and T is an integer. And the question is there a subset T such that if I sum all the members of the subset, I'll get this small t? Getting it? Wait, so if you cannot find a certificate for the no instance, does that wait? So if you cannot find a certificate for the no instance, does that mean only the yes instance of Hamilton path is in NP? Ham path is in NP? No, no, no. Oh, okay. It's good that you brought it up, Rosalind. Thank you. So I have loosely defined NP here, but the actual definition is an if and only if. Okay, L is in NP if and only if there is a um, polynomial size certificate. There is a poly size certificate and polynomial time verifier V such that V verifies the certificate. Let me call it Y. Okay, V taking the input and the certificate can verify it and say yes, okay, gives true. Okay, in polynomial. Look at it that it is an if and only if definition. Okay, this is an if and only if in the definition. What does if and only if mean? Okay, bring it down. Oof. One moment. Okay, what does if and only if mean? If I negate both sides, okay, it will still be true. Not in NP. If and only if there does not exist a polynomial size certificate. Okay, and certificate blah 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 and such that V of xy is true. Okay, so that V of xy is true, and if you bring the negation inside, then you'll get this as false. Okay, I'll get into it when I talk about polynomial hierarchy. But okay, to answer your question shortly, if you cannot find the certificate for the no instant, it does not mean that only for the yes instance AMPath is in NP. Okay, because NP is defined in such a way that if you have a certificate for that particular input which belongs to the language, then it is an NP. Okay, if the input does not belong to the language itself, okay, if the input does not belong to the language itself, then there is no question about a certificate. Okay.
I think
Yeah.
instead of L, it should have been X then. What you are saying, so it should be like
Okay. Yeah. Right. Sorry. Yeah. Good that you pointed out here.
X element of the
Yeah.
language.
Yeah. Sorry for the confusion. X is in L. X is not in L. L is in NP. Yeah. Now it will make sense. Yeah. Thanks. If X is in the language, then there is a polynomial size certificate. Blah blah blah. Okay. And we've not brought the thing yet inside, negation inside yet. Okay, so if it is not in the language, okay, X is not in the language, then there does not exist a polynomial size certificate. Okay, got it? Okay, got it. Right. Okay. So yeah, the answer is in the definition, final definition. Okay, thank you. Yeah, subset sum. Okay, and so subset sum. Okay, now what kind of sets belong to this? So, for example, if my first set S is 1, 2, 3, 5, and here I have say 7, this is my T, then can I find a subset T, okay, such that when I sum all its elements, it will be equal to 7? That is the question. And yes, if I choose my subset T, set T to be, let's say, 2, 5, then 2 plus 5 is equal to 7. Okay, and let's say if my set is something like 1, 3, 7, 1, 3, 5, okay, and here I have, let's say, 11. Is this in subset sum? Question is this in subset sum? Is this input in subset sum? Can I choose a subset from here such that it will sum to 11? Yeah.
Yes, so this the subset is in NP. Yeah. I mean, what's the problem? There was
How come?
so there was some yeah. So what was the question? Can you please repeat the question because I could not hear the problem.
Yeah, is this input in subset sum? That is, okay, equivalently, can I choose a subset from here which will sum to 11?
Okay, so see,
Rosalind says yes. Or Rosalind, can you state what is the set you are choosing? Yeah, go ahead.
since the sum here is 9 and 9 is not equals to 11, and moreover if I try to find all the subsets whose sum is a given number, so I'll have to explore a large number of the possibility that could be one. But if you give me the subset, then I can easily verify whether the sum of the subsets is equal to the given number.
Yeah, no, that is fine. But I'm asking about this particular example.
Okay.
Okay, so this is no. I'm asking about this particular example.
Ans-
Yeah,
Answer is no. Answer is no. Like in this case, 8 subsets are possible and none of them will sum up to 11.
right. Because what is the largest sum possible? It is 1 plus 3 plus 5, which is 9. Right. And you cannot hope to possibly reach 11. Okay. So this is not, the answer is no. I mean, the largest sum you can take, largest sum is 9. So this is not 11. This, you cannot hope to reach 11. That's why no. Is this clear? Rosalind, is it clear? Yeah. Yeah. Okay. So yeah, like Goel, you were saying, uh, is this an NP? This is an NP. The answer is yes. What is the certificate for any such set to be in NP? Any such input to be an NP? Sorry, what am I saying? What is the uh, certificate for any such input to be in subset sum? My claim is that subset sum is an NP. Is an NP. So given any x, or let me call it, given any s comma t which belongs to subset sum, you give the certificate as the satisfying subset. Exactly. Right. So for this, there should be a certificate. And if it does not belong to the subset sum, it does not have a certificate, right? So what is the certificate? The certificate is simply T, okay, such that, again, the same definition. I know it may seem trivial right now, but we'll look at an example which is not trivial. Okay, I is in T, I is equal to the sum. Okay, this is clear, right? So this is a certificate, and of course, if it does not belong to subset sum, you can never hope to find a subset which will, again add to T, and therefore you cannot find such a certificate. So that is kind of obvious. Now, okay, so this is another trivial example, right? Now let's go to and it'll obviously polynomial because the set given itself is of the set we are choosing is smaller than the input that we have. Now let us look at this question. Composite, comp, okay. Comp is the set of all x's, okay, all the inputs, all the x, where x is a binary representation of a composite number. In other words, what is the equivalent way of looking at it as a problem? Given a number in binary, can you check whether it is composite or not? Now it becomes slightly more non-trivial. Okay. Comp, okay, is all x, okay, such that x is composite. Mind that x is given in binary. Okay. X is composite. Now, can you say whether composite is in NP or not? In other words, given okay, sorry, I'll just leave it at that. Is composite in NP? Now, can you find a certificate for compositeness? Let's say I give you a number. Let's say there is a number which is composite, and let's say Suraj tells me that 8 is a composite number, and I tell Suraj that I'm not convinced. How do you convince me? That it is composite.
So my point is,
Yeah.
so my point is that if a number is not prime, then it will be composite, and the primeness of a number can be checked nowadays. Can be checked in the polynomial time because of that AKS algorithm.
Yeah. Okay. But that is like killing a fly with an AK-47. So yeah, right. But that okay. Nice answer. Okay. Okay. Yeah. Okay, but let's say I have a okay. So good. Suraj is saying divide by a number till 8, except 1 and 8. Okay. Divide by number till 8. Okay. How about 178? Okay, let's say you tell me that the this number is composite. Okay, how do you convince me that this number is composite? New question. You want to convince me in a simple answer that this number is composite. Okay, and I can do some kind of some simple arithmetic task. So I am a simple verifying machine. How do you convince me? Yeah, go ahead.
So 178 to show that 178 is composite. So yeah. So if I want to show it is composite, so I need to find its divisor
Okay.
So
what will you give me as a certificate? How will you convince me?
So I will give you a number which is not 1 and the number itself, And if any number in between 1 and the number itself can divide this number, so then the number is the composite one. That will be the
Okay.
set.
Good. Okay, good. Yeah. Rosalind saying, trivially, if the binary represent ends in 0, it is composite. Okay, we can do that. Else check divisibility up to square root numbers. Okay. You are all coming up with algorithms to solve this problem. Okay. Since the beginning that I asked this question, all of you are trying to come up with algorithms to solve this problem. I'm not asking for an algorithm to solve this problem, but good anyway. It'll show that it is in P, right? Or does it? No, it does not. Okay. So, okay, I want to enter this zone. Okay, in a while. Okay. Firstly, yeah. How do you convince me it's composite? Give me a divisor, a factor of this number. For example, you give me something like 2, or say something like maybe 4 will divide it. I don't know. 4, let's say. No, 4 is not going to divide it. 8 plus 8, 16. Okay, so let's say 2 divides it, and this is enough. Give me a divisor 2, and you tell me to divide it myself. Okay, and I'll divide it. I'll do the long division method, which does not take much time. Okay, but binary, I should do the long division in binary, which is also possible. And I'll do it in polynomial time, and then I say, yes, you have given me a valid certificate. Okay, so this is a valid certificate. Another certificate you may give me is a factorization. Another certificate. What do you give me the factorization as? Well, let us try dividing. 2, 8, 16, 2 9s are 18. Oh no, 16. Yeah, 2 9s are 18, and then I have. Sorry. I'll just do it this way. Divided by 2, right? 2 is a 16, 2 9s are 18, so 89. And is 89 a prime number? I think so, right? Okay, so another certificate is a factorization. You give me 2 and you give 89. And I'll multiply them and I get 178. Then I'll say, yes, now I'm convinced. This is not composite. Yeah, sorry, this is composite. Okay. Yeah, well.
Yes. For other ways, we can think in terms of the GCD also, like say, no, that won't work, I think. So I was trying to find the GCD of this number based.
Yeah, you could possibly give me a GCD also. Right, you just give me say GCD between 2. You need to give me the number and the GCD both, and then I'll do the GCD between this and that number and 178 and obtain that particular GCD, and then I can say, yeah, it is composite. That is also possible, but internally it is using the same divisor idea.
Yes.
Right?
Yes.
Okay, good. Okay, I'll quickly enter this zone. Okay, because I want to confirm one thing. Okay, now let's say now I ask you the question: come up with an algorithm to solve this problem. That is checking whether a number is composite or not. So, see, both of you have already. Suraj says divide the number till 8 except 1 and 8. This is one algorithm. Rosalind says trivially if the binary representation ends in 0, composite. That is true. It is an even number. Else divisibility up to square root n numbers. Okay. Another algorithm. One says if I am given a number n, then divide by 1, 2, 3 up till n. And Rosalind says I can do slightly better. I can do divide by 1 till not 1. I think 2 onwards till root n. And here I think Suraj says n minus 1. Right. Okay, good. Now tell me, is this a polynomial time algorithm? Both. Okay, any of them. This is algorithm 1, this is algorithm 2. Yeah. Now we are not asking about NP, we are asking about P, right? Because we are asking you to solve the problem, not just give a certificate. Okay. Yeah, or just tell me what is the running time of these algorithms. Suraj, Roslyn. First one should be polynomial time, right? The first one is okay. You mean it runs in order, say n minus 1 time or order n time, and by that logic, yours runs in order square root n. Okay, Suraj has written order square root n. That is correct, and this is also polynomial only because this is less than polynomial, so it is polynomial. So this is n to the half, right? And it is polynomial on n. Okay, good. Okay, this is polynomial on n. But what is the length of the input? That is the question. Yeah, go ahead.
Yeah, but then the number itself could be exponential. So, like say if n is exponential in itself, and if I take the square root of the exponential thing, then the result would still be an exponential.
No, but we are talking about the input itself. So let's say given n, okay. So I'm doing everything in terms of n. Okay. What do I mean by the let's say what do I mean by polynomial with respect to the size of input? What do I mean by that? I
So size possibly would mean the number of the bits required to represent that
exactly,
number.
exactly. By size of input, I mean number of bits needed to represent it. Okay. Now, given n, by n I mean a natural number. But how many bits do I need to represent it? For any number, natural number n, how many bits do I need to represent it?
Log n.
Log n, right? Binary representation is log n. Okay, so this is the actual input size. This is the actual input size. Because in the Turing machine tape, you'll give me this log n, which is m actually. So you should be giving an algorithm which is polynomial with respect to m. Need an algorithm running in poly m time, not poly n time. Getting it? Because what do I mean by the size of input? It is the number of bits needed to represent that input. Okay, and so what is order n? And okay, and binary representation will take log n. So what is the relationship between n and log n and m? Is that I'll take 2 to the log n is at most m. No, sorry, 2 to the log. What am I doing? Okay, actual input size is m. If I say order n, then n is anyway taking log n bits to represent it. Okay, which will mean it is order 2 to the m. Okay, because m is equal to log n, which means 2 to the m is equal to 2 to the log of n, which means that n is equal to, this is nothing but n. Okay, or I'll write below, which means that 2 to the m equals. And this is running in time how much? Order 2 to the root m. Getting it? It looks polynomial, but it is actually running in exponential time. Is that clear? Rosalind, that is clear. Suraj, Sagar, said clear. Good. Okay. Saga is also good. And Goel, you're fine? Sair is also good?
Yes.
Yeah.
Yes.
It is actually, under the covers, it's actually running in exponential time. So this is why actually composite and prime were such huge problems for a long time. And like Goel pointed out, it was prime, primes, composite, primes is nothing but composite complement, if the number is not composite, it is prime, okay. So anything that is not in the composite set is a prime in the prime set. So and question now if you obtain a polynomial time algorithm for composite, P is closed under complementation. P is closed under complementation means that you can obtain a algorithm for primes also, right? So we didn't know an algorithm for either of them. Okay, a P algorithm, polynomial time algorithm for either of them. As you can see, we know only exponential time algorithms, We knew it was in NP. We were not sure whether it is NP complete, and we did not have a P algorithm for this. Getting it? And in 2006, there is the famous result called AKS primality test. Okay, and they showed that actually primes can be solved in P. Is in P. It has a polynomial time algorithm, and they use some algebraic techniques to do it. And this AKS actually stands for Agarwal Kayal Saxena. They used to be students of Manindra Agarwal, and they were folks from IIT Kanpur. And this was a huge result in complexity theory. That time, it even won the Gödel Prize, which is the largest prize you can win in theoretical computer science. Okay, and it is a result of this century. But yeah, so I just wanted to show that obtaining a polynomial time for checking primality is actually not that simple. Okay. Okay, good. Now we'll dive more deeper. Yeah.
I have some related question here that since
Yeah.
most of the problems which are there in NP are NP complete, so what makes this problem, this primes problem, not NP complete and somewhere in between, it used to be considered as somewhere in between P and NP complete kind of.
That's right. Um, well, I mean that is a very high level question. It is outside the scope of this course, and it is not clear actually, Goel, what the reason is that it is actually making having this kind of situations. But okay, I'll tell you some things. Okay, I'll tell you there is something called NP intermediate problems. Okay, mediate problems. Okay, and there are folks like graph isomorphism and several kind of things here, and you have NP complete problems, which are like SAT and click and so on. And then you have P, obviously. So they are sitting like this. So P is the small guy here, and NP intermediate is here, and SAT and all are here. Now there is some cutting edge research going on here by folks like Guru Swami. Okay, there is a computer scientist called Venkat Guru Swami, and he has some work in CSPs. Okay, and he has actually tried to develop a measure, complexity measure, okay, as to why something is in here and something is NP intermediate and something is in P, and you can try checking out his work. Okay, but this is a bit too out of scope for this. Okay.
Yeah. Thanks for this information. I'll check it out.
Great. Okay. Great. Anyway, let's come back. Okay. Good. Now let's see. The final problem is this: primes. Okay. Composite, we showed a certificate. What is the certificate? The factorization or a divisor or whatever. Now is the interesting thing. How do you show a certificate for prime? Or can you show a certificate for prime? That is another question. So prime is, so this is the question. Prime. Okay. It is all those binary representations of a natural number. X is prime and X is in binary. Now can you tell me, if I want to show prime is an NP, what is a certificate for it?
So it is easy to show the certificate for the composite number.
For composite, it is easy. For the no case, it is easy. Yeah. To say no, it is not prime.
No, yes. So like in this case, it would be easy for the yes instance. It won't be. I mean, for composite, it is for composite to show the yes instance was easy, and for the primes to show the no instance would be easy.
Right. That's right. Good. Because why? Because prime is in co-NP. That is exactly the definition of co-NP. The fact that composite is an NP, okay, would imply that prime is in co-NP. So you have NP here, you have co-NP. Okay. You have co-NP here. Now if composite is here, then definitely prime is either here or here. Question is, now since it is here, it is easy to say no, because it was easy to say yes there. Okay. Question is prime here? Is prime also in NP? Is prime in NP intersection co-NP? Or is it, can you not show it, or is it not known yet, or something like that? But coming back to the question, what is the certificate for it? Let's say you give me a prime number. Okay, let's say Rosalind this time says, okay, sir, 41 is a prime number. And I tell her I'm not convinced. Tell me, why is it a prime number? Before, you were giving me a factorization, right? Before, if Rosalind were to say, actually, let's say 42 is composite, then I'll say why, and Rosalind will say, oh, she'll give me 6 and 7, and she tells me just multiply them. I'll multiply them. I'll get 42. I'm convinced. This is my certificate. I show that all primes less than 41 cannot factor 41. Okay. You'll show that all primes less than 41 cannot factor 41. So you'll give me all the primes which are less than 41. Right, Rosalind? Huh? Yes, you'll give me all the primes which are less than 41. Say 2, 3, 5, 7, 13, and so on. Right. And how many primes exist? A lot of primes exist. And a lot of primes exist here. And you'll give me all the primes, and I then keep checking, and again by that same binary length argument, sadly, this will turn out to be exponential. Okay, Rosalind give a sad face. Okay, so right.
If the counting is the problem, then I have a better way to show. Yeah. So if I give you the if you give you the value of the factorial of the 40, and if I show that factorial of the 40 plus 1 is not divisible by 41, so then 41 is a prime number, and this is a statement of the Wilson's theorem, I guess, that P is a prime number if P perfectly divides 1 plus factorial of P minus 1. So as a certificate, I will give you the value of the factorial of 40.
Nice, nice. That's a nice. I okay. So yeah, you can use this theorem. But what is the size of the factorial of 40?
So certainly the size would be pretty long, but then the count won't be much.
Yeah,
Uh,
we'll reduce on the count. We'll reduce on the count. That is right. But we suffer on the size. But good. Nice. The count will be pretty large actually, because what is 40 given n factorial? It is nothing but n times n minus 1 times and so on and so forth, which will be some n to the n, upper bounded by n to the n, which is like something like 2 to the n log n, which is also exponential. And in fact, we have an exponent over this because it's represented in binary. And so we have 2 to the 2 to the n log n. Something like this is the size of, if I need to write this. And here the problem is that I have too many of them. Okay. So, okay. I will, yeah. Go ahead.
because we require a certificate as inside the size of the certificate should be polynomial.
Should be polynomial in size. Okay, good. Good, right? Okay, so I'll not tell you the final solution because it is a bit non-trivial. If you want, maybe next session, but it'll take a long time to actually explain it probably in full. But it is possible to show that primes is in NP. Okay, by something called a Pratt certificate. There's a mathematician called Pratt. Okay, and he has given a kind of certification for. He has given a theorem. Okay, that says that okay, if your number is prime, then your number will have a certain structure. I forgot the exact statement. Okay, but look this up. Okay, after the lecture ends, I'll add a link here. Okay, in the same document regarding Pratt certificate, and it is not straightforward after this. Okay, because the statement is as follows: that if your number is prime, then there exists smaller primes in which will divide a certain number which is related to this prime. So you can see, right, the Pratt certificate contains more primes in it. So I need to check whether they are primes, and then I need to check whether, and if I need to check whether these smaller primes are primes, then I need to find another certificate for it. So this is an idea of recursive certificates. Okay, so your certificate will contain another certificate and contain another certificate and so on, and you can actually argue that the size of the certificate is not very large. Okay, the size of the certificate is not very large, and so you can look this up. Actually, the problem, the difficulty in this proof is actually with the technicalities, the numbers, but the general idea is very simple. Okay, but yeah, you can actually show that primes in NP. What is the key takeaway? That primes is actually sitting here in NP intersection co-NP. It is not isolated right away to co-NP. So that's why the next big problem was P is here. Is prime inside this? That was the next big problem, and it was solved by that AKS primality test. Okay, so is everyone good with this?
This at the intersection of NP and co-NP we have P, and which is an
oh sorry. Yeah. What? P is sitting somewhere inside here.
Yes. And apart from P, something else is also there. And which is an open problem, I guess. That
which is an open problem.
Yeah. So do we have any other problem except prime and which is at the intersection of the NP and co-NP and which is not there in the P?
Yeah. Wait, there's an interesting problem there actually, but I cannot recall right now. Sorry, that is an interesting problem. I'll tell you. Okay, I was thinking about it not long ago, but yeah, good question. Sorry, a problem which is in NP intersection co-NP. That's what you mean, no?
Yes.
Besides
and which is not there in P, which is
not known to be in P. Yeah, there is. But I cannot recall it right now. But there is a well formulated nice problem which is there. Okay.
Yeah.
Okay, is everyone clear with this? Can you repeat? Okay, what? The Pratt certificate? Yes, sir. Okay. So, okay, I'll just take a detour. Okay. And here I'll look up Pratt certificate. I'll give you the exact theorem here. Okay. Primality certificate. And here, okay. So, actual theorem is by Luca's theorem, right? And this is the theorem. Suppose we have an integer a such that a to the n minus 1 equals 1 mod n for every prime factor q. It is not the case that a to the n minus q is equal to 1 mod n, then n is prime. That is what they are saying. Right? Oh no, I switched off. I need to share again, I think. Okay, right. This is the one. And then n is the prime. Then n is prime. Now look at the statement here. Now you might think that okay. You might think that okay, fine. Where did it go? Yeah. Now, Rosalind, I'll just paste it here. Now, this is a theorem, okay? It says, okay, it says if n is a prime, okay, so it goes as an if and only if, okay. If n is a prime, then there will be such an a, and for every prime factor q of n minus 1. It is not the case that blah blah blah. Now, you may say that, okay, first of all, the certificate would be I'll give an A. Okay, I'll give such an A. This is my certificate. I'll give an A. And I'll give every prime factor q of n minus 1. Each prime factor of n minus 1. This is my certificate, and then I'll check whether this is true. This is what it is actually. This is exactly what the proof is. Now, problem is I need prime factors of n minus 1. Then you'll give me some prime factors. Now, how do I know that these are the prime factors you gave are indeed correct? My verification algorithm should actually also check, since it needs to check whether the certificate is valid, it also needs to check whether these prime factors are indeed prime factors, right? And not just factors. Factors I can check by just doing division, but my algorithm needs to check whether it's prime or not again. So each of these are prime or not. How do I check it? I come back to the same problem, right? And how do I deal with this? Getting it? Yeah, getting it. So how do I check whether these are again prime? Well, I'll include the same Lucas theorem certificate again. So for each of these prime, I'll include another A, let me call it A1, and then prime factorization of A minus 1, A1 minus 1. And now this will contain another prime factor, set of prime factors. I need to check whether those are prime or not. Then I'll again expand this, and this is a recursive certificate, and you can actually prove that this certificate is not very large. It is polynomial in size. Getting it? So you may have seen recursion in data structures algorithms, kind of. So this is an example of another recursion. Yeah. Okay. Good. Thank you. Okay. So a lot of theory we discussed. Okay. So. Okay. So I think this is you can work out this. I think so. Rather, I would discuss this. Okay. So polynomial hierarchy. Okay, and then we'll possibly come to the previous questions if we get time. Polynomial hierarchy. So, firstly, P. Okay. When is a language said to be in P? Well, if X is in L, then, okay, if L is in P, then there exists a Turing machine, deterministic Turing machine, running in polynomial time. Let me call it V. Okay. Deterministic Turing machine, which is called V, running in polynomial time on the input, such that for any input X is in L, X is in the language, if and only if V, when given input as X, accepts. Right. V, the Turing machine, when given X, accepts. Okay, good. We all agree with this definition. We know this is the definition of P, just writing with some fancy mathematical notations. Now, when is a language in NP? Well, I can write there exists non-deterministic Turing machine and so on and so forth and the same definition, but we know that there is another nice definition for NP, which is using the verifier notation. And how do I do that? I just say there exists a deterministic Turing machine, again V, which is the verifier right now, running in polynomial time, such that for all X in sigma star, if X is in the language, then, okay, there will be a certificate, let me call it Y, such that this verifier will take the input as well as the certificate and will accept. If it belongs to the language, if it does not belong to the language, it will not accept. This is the definition of NP. Agreed, right? Now, what is the definition of co-NP? Okay, co-NP. Again, there exists a deterministic Turing machine V running in polynomial time, such that X is in L if and only if give me any certificate, okay, for all Y, V of XY accepts. This is another definition of co-NP. If you've seen the lectures, okay, I'll just quickly mention that a co-NP definition can be said to be, you remember this, right? If a language is an NP, if it accepts on an input, there is at least one accepting path. A language is in co-NP if there is a machine where all the input path, all the computation paths accept on their input. Okay. If try to work it out. Okay, if you're not convinced, but yeah. So yeah.
I think that here it's true that if X is the element of the language L, then for all Y, V of X, Y accepts. Other it should be V star or something else, because V of X comma Y will reject. However, we can always take its complement kind of a thing.
Yeah. By V, I mean different V's here. That's what you mean, no? This V is not same as this V and not same as this V.
No, all the first three V's are same, but then the last V should be the different one, because...
No. Because, see, this is a language in P, this is a language in NP. For all we know, this language may be different from this language. So the same verifier may not work. That's why I'm saying, I'm notating them as V only, but they mean different Turing machines for different purposes.
But in the case of the co-NP, if X is the element of the language, for all the yes instances, I mean, we need to explore all the yes instances, and for all the yes instances, the thing should get accepted. Yeah,
Right. All the computation paths are going to accept, and that is true that we need to check for all of them if we are running it deterministically. But by a certificate definition, what we mean is that if you give me any of these certificates, I'm fine with it. That is, for all of these certificates, I should be accepting.
Yes.
right? Okay, good. Now, yeah, so good point. These are different machines. This is for P, this is for NP, this is for co-NP. Okay, so there's no relationship between this V and this V, at least for now. Okay, I'm just doing it for ease of notation. You will see why. This is because now we talk about the polynomial hierarchy, which is what if I extend this notation? Okay, what if I extend this notation? What if this for all there exists? Okay, I extend this notation. That is, suppose I come up with a language. Ah, yeah, okay, I'll write it in red. Suppose I come up with a language that is x is in L if and only if there exists y1 for all y2 v x comma y1 y2 except. You can see that I've added a there exists here, which is different from everything before. Here there was a single there exists, here there was a single for all, here there is one there exists, there is one for all. Okay, now what have we created? We've created a language which is possibly more difficult than NP or co-NP, and this is what is called sigma 2. Then there exists again a deterministic Turing machine V running in polynomial time, and so on and so forth. This is called sigma 2. Similarly, I can write L is in pi 2 if I have for all first, then there exists. Okay, then there exists V running in polynomial time. X is in L if and only if for all y1 there exists y2 V of x y1 y2 except. Why to come up with such a situation of having two y's? Yeah, we'll come up with examples. Okay, cool. Because there are languages where you cannot formulate without two y's. That is the simple answer for it. I mean, at least you've not found a way yet. There are some languages where you don't know how to come up with fewer y's. Okay, I'll give you a more. Okay, sure. Now this is it, right? Now so if for all is at the beginning, then it is in pi. If there is exists at the beginning, then it is in sigma 2. Okay. Now I can generalize it sigma k. Okay. L is in sigma k. Again, if there exists blah 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 v. Okay. Such that x is in L if and only if, since I am in sigma, I should have there exists first. There exists y1 for all y2. There exists y3 and so on, so forth till it could be a there exists of for all. So I'll call it q. Okay, yk and v of x, which is the input, main input, and all the list of certificates x, y1, and so on till yk. This is a generalization. Okay. Now I can do the same for oh, I can duplicate no. Okay, I can do the same for pi also. Pi k, there exists so on and so forth. This is for all this time, and this is there exists. This is for all, and okay, I just want to check if recording is happening. And this, okay, and this q may be there exists or for all, and this q, this guy could be there exists or for all, anything. Okay. Now observe that NP, what is NP? Now if sigma k, okay, is k levels of their existence for all, and pi k is k levels of their existence for all, NP just has a single there exist, and co-NP just has a single for all. So what does it mean? NP is nothing but sigma 1. And what is co-NP? Co-NP is nothing but pi 1. Right? Because sigma k means k levels of for all, there exists followed by there exists for all, there exists for all, and so on. And there is only one there exists, and that's it. Then it isn't sigma 1. It is exactly equal to sigma 1 by this characterization. Furthermore, if L belongs to NP, then L complement belongs to co-NP by definition. Okay. Let's say L is in NP. Okay. Then L complement belongs to co-NP by definition. Right. So L is in NP means what? X is in L if and only if there exists Y, V of X comma Y. And by the way, each of these yi, y1, y2, and so on should have polynomial size. Okay, R of polynomial size, because we are continuing the certificate definition. The certificate, remember, should be of polynomial size. Okay, and so there exists y, v of xy, except, right? Now what if x is not in L? Then I can negate both sides, right? There does not exist y for all v of xy, except. But what is this? What does it mean that there does not exist? This is a discrete mathematics exercise, that you can push the negation down and make it for all. In other words, if I say there does not exist, I can say, so if you say there does not, it is not true. Okay, yeah, it's rather this. It is not true that there exists a bad boy in this class. You can say, for all the students, it is not true that the student is bad. So this is a discrete mathematics exercise. You can push the negations inside. Getting it? So let's say y is an apple. So it is not true that there is a bad apple. Okay. And it is not true that there is an apple which is bad. So you can say, for any apple, it is not true that the apple is bad. So it's the same thing. If you push the negations inside, you can change a for all to there exists, and there exists to for all. And now this can be done in polynomial time, as we know, because p is equal to p complement, right? Because this is nothing but a p thing. Okay, without any for all there exists, it is just p, and therefore you can write it as a v prime xy. Okay, and this is nothing but a definition of point p. I can extend this definition. So I can say that if L is in NP, if L is in sigma 1, sigma k, then L bar is in pi k. Using the same logic, I can push the negation gates inside. Goel, you had a question that time?
No.
Okay.
It was clear.
Sure. Okay. So you have NP here, you have co-NP here. They intersect in NP intersection co-NP. Now by definition, NP is equal to sigma 1, co-NP is equal to pi 2, and NP is contained in sigma 2, and co-NP is contained in pi 2. This is trivially, okay. You just don't set one of the quantifiers, and you just keep a dummy quantifier. Yeah.
Co-NP is equal to pi 1. Some typing mistake here.
Oh, sorry. Co-NP equal to pi 1. Yeah, thanks. Okay. And you can even show this this and you can show this. Okay, you can try it out. And sorry, you can show that they are equal to some intermediate, and which is called delta, which we need not deal with right now. Delta 2, and so this means this is delta 1, and this is both contained in sigma 3, this is contained in sigma pi 3, and this and intermediate, there is delta 3, and so on and so forth. What is this called? This is called the polynomial hierarchy. What we are trying to do is we are trying to come up with languages that are more difficult than NP. And it seems like these languages are much more difficult than NP. It seems to be so. If someone proves, an interesting thing is that this is a huge hierarchy, right? There is an entire tower of sigmas and pi's. If someone proves that P equals NP, then you end up proving that polynomial hierarchy, the entire polynomial hierarchy collapses down to P. Okay. And this is an open problem, obviously, because it's not proved whether P is equal to NP or not. But this is a good evidence that probably P is not equal to NP. Because if P equals NP, then all these difficult languages automatically suddenly become easy.
Will it be okay to say that everything will collapse to NP?
It will also be okay to say that everything will collapse to NP. That's right. Because if it collapses to P, and we said that it is proved that P equals NP, then obviously it will collapse to NP also, that equivalently. Okay. And there are a lot of theorems that talk about cases when this polynomial hierarchy will collapse. These are called collapse theorems. And but yeah, so the entire polynomial hierarchy will collapse. And each of these languages in classes in complexity theory can actually be characterized by these kind of propositional statements with for all there exists, and not, and, or, and so on. And there is an entire field called descriptional complexity dedicated to it. Okay. Yeah. So that was the introduction to PH. Now let's quickly look at this. What can we say about the position of the following languages in polynomial hierarchy? Okay. Exact click. Okay. Exact click is given a graph G and a number K. What is the largest such that the largest click in the graph G is of size K? Okay, I've already written the answer here, but let's remove this. Okay, so largest click of graph G is of size K. Okay, what is a click, by the way? A click is a complete subgraph. There is a subgraph where there are edges between all the vertices in the subgraph. Okay. Now look at this problem for a while. Stare at this. Okay. I'll give you 1 minute. In fact, I'll give you an example.
So will it be in sigma 2 or pi 2? Because I need to show that whichever click I select, that click would be, the largest click would be of the size K. So
right, that is the question.
I think for all quantifier will come in the beginning.
Okay.
And then the existential quantifier will come. So I think it should be in pi 2.
Good. Okay. Okay, sure. We'll let the others also think about it. Okay. So I'll give you an example here. Exact click. Oh yeah, what am I? Is G3 in exact click? Is the largest click here of size 3? That is the question. So what is the clique you can find? Well, you cannot make a clique out of these 4 because this edge is not here. You cannot make a clique of these 4 because this edge is not here. So finally, you need to choose a smaller complete subgraph, and this is the smallest the smaller complete subgraph. And since you could not make a clique of size 4, the largest clique is of size 3. So this is an exact clique. What about G3, G2? The answer is obviously no, because I can make a bigger clique. I can make 3 is a clique. Sorry, because size 3 clique present. They are talking about the largest clique. Obviously, I can make a 2 clique. Okay, 2 clique is nothing but an edge. Complete graph on two vertices, which is nothing but an edge. There are edges here, obviously, but I can make a bigger clique. No, we are talking about the largest clique, and obviously G5 is not there because obviously largest clique is 3. Okay, so Goel says that to characterize this, I need for all there exist. Okay, and do any of you have any ideas here? Suraj, Rosalind, any idea?
So now I changed my mind, and this in fact is in sigma 2 because there exists a sequence of the vertices for all clicks possible, wherein the largest click would be of the size P only. Uh, we cannot find a solution better than 3. So I think it would be in sigma 2.
It's in sigma 2. Previously you said pi 2.
Yes, yes.
Okay. Good. Okay. Rosalind says, can we think along the lines that the number of subsets would be 2 to the v? But now, Rosalind, you are trying to create an algorithm for this. We don't even know. I mean, first, our aim is to first check if we can hope to build a polynomial time algorithm and then try to build an algorithm. Okay. So first we are trying to categorize it, okay, in some kind of polynomial hierarchy. Okay. So obviously first try would be, is it in sigma 1? Okay. Yeah. Okay. Not bad. So first try, let's do your approach, Rosalind. Can we think along the lines of number of subsets would be 2 to the power v? 2 to the power v along those lines, yeah, order 2 to the power v. We can do slightly better maybe. Number of subsets, oh yeah, we can do much better actually. N choose k. No, yeah. So k, if k is of order n, then we are sunk. Yeah, it will be some exponential, that's right. So that's why if we go across all possible clicks of size k, okay, where gk is my input, okay, gk is whether my graph has the largest click of size k. Okay. Now recall the click problem. What is click? Click is in NP. In fact, it is NP complete. What is click? It says given gk is k size click in G, but now we've changed the question to the largest click, remember. Okay. So if you use the click NP, okay. Oh, okay. Yeah, okay. So if you use the click algorithm, okay, like you said, Rosalind, what is the click algorithm to show it is an NP? You can think of it in 2 ways. First is the certificate is the click I give you. Okay. Click is an NP. How? Certificate is the click. right? Another way to show click is in NP. Alternate method would be non-deterministically choose a set of vertices of size k and then check if it's click. These are both the same thing. I hope you can see. These are just the certificate definition and the non-deterministic tuning machine definition. Right. Now, my problem is exact click. I need to check whether it is the largest. Now, if you give me, let's say, the click, if you give me the particular click which is the largest, how do I verify whether this is the largest click or not? Okay, I verify it is a click. Okay, your claim is that this is the largest click in the graph. Okay, and it is of size k. Firstly, the first test I can do is it of size k? Let's say that is true. Next, I can check is it a click? That takes polynomial time. Great. Now, is it the largest? Now, how do I check whether the click that you gave me is the largest? Well, I need to check for all the clicks that are larger than it, right? So we again have to enumerate all clicks and compare. Good, right? And all clicks that are larger than that particular click, right? And then keep comparing and check whether it is larger. This same, right? Good, good. I hope you can notice that the same certificate for click does not hold for exact click. Because now it will take me a lot of time. I cannot do it in polynomial time. Is this also exponential? It will take exponential time, yes. Because I need to check across all clicks which are greater than k size and choose some greater than k. Which is n choose k plus 1, n choose plus n choose k plus 2 and so on till n choose n. And if my k is something like n by 2, I'll again get exponential. Right? So this same certificate does not work. I hope you can see. So now, we were trying to put it in NP, right? So the question is it in NP or equivalently is it in sigma 2? That is a sigma 1 because NP is sigma 1. Now another question is, can we say that it is in co-NP? Now that is a very strange question to ask because this language does not easily fit inside co-NP, okay? And usually to fit something inside co-NP, you first ask if it is in NP and then ask whether it's in co-NP. I mean, ask it as an NP and then try to come up with a complement of it, okay? And so exact click complement would be something like, the smallest, not smallest.
Will it be independent set, the complement of click?
Yeah, you'll need to show that exact click is in co-NP. You'll need to show that exact click complement is in NP, right?
So which problem would be the complement of click?
Yeah, the complement would be something like G. Okay, G, largest click of G is of size K. Then we'll say the largest click of graph G is not of size K, right?
Largest click of the graph of the node of the size not K, or the negation of the click. I need to take the negation of the click and I keep K as it is. So will it mean that the largest set of the vertices which are not of the size K, wherein none of the vertex is connected to any other vertex? Because in case of the click, every vertex is connected to every other vertex.
Oh, no, I mean, we don't need to go that low level also. We can just say not click, right? If you say not click, that is enough.
Okay.
Obviously, if you say not click, it means a set of vertices which are not connected to each other and so on. But we don't need to go that far down the tree.
Okay.
As long as you say there does not contain a click, that is enough. But yeah, that is true. Okay. Yeah. Okay. Okay. So it is. So we don't know whether it's in co-NP or not yet. Okay. Let's try a higher level. Can we say that it is in sigma 2 or pi 2? To say that it is in sigma 2, I need to show that X is in L if and only if, okay, first of all, if you to say that there exists a verifier V, okay, and then you need to say there exists an L if and only if there exists Y1 for all Y2, V of X, Y1, Y2, except. This is what you need to show, right? To show it's in sigma 2. To show it in pi 2, you need to do for all Y1 there exists Y2, Vx, Y1, Y2. Let's try this first. Now, let's try to formulate this problem in terms of there exists and for all. We are saying if G belongs to the language, GK belongs to the language, then the largest click is of size K. Equivalently, we mean if we take a set of vertices which is larger than this particular size, let me call the click as H. If we take any set of vertices which is larger than H, I will not be able to find a click. Otherwise, it will contradict the fact that this set of vertices is largest. I hope you can see that. Again, if I choose, if H is the largest click here, okay, and if I take any set of vertices which is larger than H, okay, which is larger than H, I should not be able to find a click, because if I find a click, then this new set of vertices will be the largest click, right? And which is strictly larger than H, and which is a contradiction because H is the largest click that I have. To repeat it final time, if I choose any set of vertices which are larger than K this time, because if K is the size of the click that I have, okay, if I choose any set of vertices which are that large, I should not be able to find a click. Okay. Right. Or equivalently, sorry, I gave the pi definition for it. Okay, equivalently, if H is the largest click here, if H is the largest click here, for any set that I choose which is larger than H, it should not, that set of vertices should not be a click. Same idea, right? So now I'll write it. There exists a set of vertices S, okay, and okay, such that for all, okay, I'll call it H, okay, such that any set that I take where size of S, the size of the set is greater than the size of H, okay, and where H is of size K, okay, then I write V of X comma, now what is X? X is nothing but G and K, right? This is my X, this is my input, and what is my Y1? H, and what is my Y2? S, except. Now, what does V do? What is V? V should be a deterministic polynomial time Turing machine. Remember, what does V do? V checks, V is a Turing machine, deterministic Turing machine. V checks if, okay, H forms a click or not. Okay. Is that clear? In G. Now let's read the problem. There is a set of vertices which is of size K such that given any other set which is larger than it, okay, given any set which is larger than it, okay, it should, okay, and sorry, so not click or not, and forms a click in G, and S does not form a click. I can check whether H forms a click by just looking at the adjacency matrix, and I can check whether S does not form a click by looking at the adjacency matrix. Right? So, given an H of size K, we can check whether H forms a click or not, which is of size K, and it will tell you yes. Okay. And if both are conditions are satisfied, first condition is H forms a click or not, and S does not form a click, which is this larger set. Okay. So this is the characterization. Is this clear?
So actually, this end thing should also be included here. Otherwise, it does not make.
What should be included?
So it should also be included that B of G comma A plus 1 comma H comma S rejects. So V of the verifier accepts only a click of the size K and does not accept all the things wherein the value is greater than K.
Okay, I did not get it. Goel, can you repeat it? Sorry.
So I mean to say that here what is happening that the verifier is accepting. So where verifier is rejecting yes, I mean there exists a click of the size K, but this does not include the fact that there does not exist a click of the size greater than K.
Oh yeah. So see, now see, I'm looking at a particular S. Okay, this is a bit abstract, but I'm looking at a particular S which is larger than H. Okay, and I'm giving it to my verifier. Now verifier just looks at that particular S and says that no, it does not form a click. I'm good, and I do so for each S which is larger than H, and it says no, it does not form a click. It does not form a click. At the same time, it is saying I give a good H, okay, which says yes, it forms a click. Yes, it forms a click, and then this combination of H and S is what my certificate is actually. Getting it?
Yes, because even if I exclude S from here, then also this verifier is going to return the true value only.
Of course, it will return a true value, but will it give? Is it the definition of exact click? No, it will give me a verifier for the click, not for the exact click. Exact click means that any larger set I choose, which is bigger than K, right? Any larger set that I choose, which is bigger than K, is should not form a click. Getting it?
Yes. So this is slightly, slightly ambiguous here.
Yeah, it's slightly abstract.
Yeah, probably verifier is taking three arguments here. The first one is the column instance, the second one is this H, and the third one is S, and three arguments are mandatory for this verifier.
Right, they are mandatory.
Yes. So
right.
it was just out of curiosity that what if the question has been like second largest or third largest kind of thing?
Oh, okay, good question. Well, second largest. Let's see. Let's look at the same definition. GK, the second largest click in the graph G is of size K. So, what you'll need to do in this kind of approach is you need to say that there exists an H. Okay, sure. You need to say that there exists an H. Okay, and then again there exists an H2. Okay, you need to say there exists an H whose size is equal to K and H2 whose size is greater than K, and then for all S whose size is greater than H2. This will characterize it, right? Well,
Okay.
And
So
yeah, again, this is an exercise in discrete maths where no, okay, this is not even an exercise in discrete maths. Since h1 and h2 are represented by strings, you can actually fuse them together into a single string. Okay, and there are a lot of examples where this is useful to show in polynomial hierarchy, and then you'll actually show that this is in sigma 1, sigma 2.
okay.
Good question.
Thanks.
All possible elements in set S is also exponential, then the verifier in total will be exponential time to prove H is the biggest click. That is true. But remember, Suraj, if you try to make it deterministic, then it is true that you need to go through all exponential to find the biggest click. But remember, we are doing a certificate definition where the verifier is assumed to give only one S. That is true, Suraj. For example, okay, I'll give you an example. For example, what is the definition of NP? X is an L if and only if there exists a certificate VXY accept. Again, I can say that verifier needs to go through all the Y to actually say that there exists to actually make an algorithm out of it. Similarly, co-NP definition is for all Y VXY accept. Right. I can say that the verifier needs to go through all Y to actually decide. Right. But listen here that we are not trying to make a final deterministic algorithm out of it. This is exactly what this is exactly the point of polynomial hierarchy, that you say that such a verifier accepts if you have a candidate from this set, these good set of Y's, these certificates, as we can say. We are rather trying to say, characterize that if I can always come up with certificates. Okay, where is it? I can always come up with certificates where I choose such an S H and choose such an S, then my verifier will verify. Okay. Secondly, if you want to come up with a deterministic algorithm which will decide exact click, it will take so much time. It will take some exponential time for this and some exponential time for this. And you see, right, this this is an example of why and you are probably trying to come up with a polynomial time algorithm for this. But if you do show that unrolling this would actually lead to a polynomial time algorithm, then you'll end up showing that p is equal to sigma 2. Getting it, Suraj? We are not trying to build a deterministic algorithm for this. As so far, we are only trying to build a verifier algorithm for this using this particular characterization. Getting it? Yes, sir. Okay, good. Yeah. So this is the descriptional complexity way of looking at it. There is another way to look at it, and it is using what are called Oracle Turing machines. But that is not discussed in this course. Okay. Okay. Just a fun fact. Okay. You can actually uh, represent chess, the game of chess. Okay, chess as a language is defined as uh, given. So we've all played chess, right? So there are chess pieces here. Okay, what we want to play is something called n cross n chess, where there are n rows, n columns, and then you have any kind of configuration: queen here, king there, and whatever. Okay, you have a chess configuration, chess pieces, mapping of chess pieces. Okay, is there a winning strategy? This is the question. This is the chess problem. Okay, and this, for example, we saw that Sudoku, that problem of numbers, okay, is in NP, right? Chess, it is not clear whether it is an NP. In fact, chess is thought of as a very difficult language because it's way up in the polynomial hierarchy. Because chess can be written as follows. Okay, X is in chess. Okay, if and only if there is a move that I can make for anything that the any opponent move. Okay, then there exists a move that I can make for any of opponent's move then I can make a move for any of opponent's move, and so on and so forth. And finally, I can verify whether that set of moves will lead me to checkmate. Just giving you a slight example. Okay. Yeah, Goel, you have a question?
No. Can you please post the reference of this wherein this chess is mentioned
Sure,
as
sure.
quite.
One reference is obviously nature of computation itself.
Okay.
You can check it out. Okay, and you can look up into internet something called TQBF. Okay, totally quantified Boolean formula. Okay, look up these
Yes.
2 points.
And
About
is Antakshari also a similar problem? Antakshari, which we used to play the names of the cities, like
hmm.
Antakshari is a game people used to play in North India.
Right. That singing game, right?
Yes. So the end alphabet of the name of the city, the other one. Yes. That's the singing name. Yeah, that's
Yeah,
what.
nice example. Yeah. So Antakshari. Yeah. Antakshari would be an example of a language in PH, polynomial hierarchy, which is not clear whether it is in NP. So, like, if Goel sings and Suraj needs to win or not, okay, that it is a very difficult problem to determine whether Suraj will win or not, something like that. Yeah, good. And this leads to the philosophical questions of puzzles versus games. So puzzles are those languages which can be characterized by NP, and games can be characterized by PH, or actually P space. But anyway, PH for now. Okay. So you can check this out. Okay. Puzzle games are more harder than puzzles philosophically. Okay. Oh, we've run out of time. Okay. Okay. I'll just ask you guys a quick question. Okay. About what the status of the polynomial hierarchy for this is. Ramsey. Okay. Okay, but this is a bit abstract question. You have a graph. Okay. You know what a coloring is, right? I can color vertices like this, but equivalently there is something called edge coloring, which is something like this. I can color the edges. Okay, there is something called edge coloring also. Now the question is saying for all red blue edge coloring of G, there is a red edge or a blue K in G. By H and K I mean subgraphs. Okay, as subgraphs. So example is, if I have a graph G, no matter what kind of coloring I give the edges, is H coloring a homomorphism to graph H? Is H coloring a homomorphism? It is an isomorphism, but for a homomorphism, you need to define what the operation is, Rosalind. So, but if you mean an isomorphism, then yeah. Right. Okay, good. So, no matter what kind of coloring you do, okay, you will always either get a graph H, which is of red color, or you'll always get a graph um, K, which is of blue color, subgraph K, which is of blue color. So this is the problem. Okay. Question is, uh, where in polynomial hierarchy is this problem? Okay, I'll bring back the problem once again. Copy this, paste this here. Can I crop it? Okay. Anyway, this particular problem. For all red blue coloring G, there is a H or a blue K in G. So can you tell? I think at this point, by reading the question, can you? I think it's kind of obvious where it is. Is it in NP, co-NP, sigma 2, pi 2, sigma 3, pi 3? Try to characterize it using quantifiers for all their exists.
So like edge coloring problem is there in NP. So therefore one of the y exists. And now we have to show that whichever certificate I pick, the one endpoint of that certificate should be red and the other one should be uh, blue.
Could be. Good.
So this will become what? So there exists a red or a blue for all edges.
No. You said the correct argument, but you flipped the quantifiers at the end. What did you say first?
So I said that there exists a red or a blue. No. For all possible colorings, there exists. So
Exactly. Good.
This would be pi to them.
Good. Right. For all colorings, and I can write it as say 5. Okay, yeah, Rosalind got it right. For all colorings, sigma, which takes in a vertex and gives a color red or blue. Okay, there is a H or K, so that so when I put apply sigma on the set of vertices H on G. Okay, when I do sigma on G, then red H or blue K will be present. This is V. Okay, and this is nothing but a set of vertices. There exists H set in V, and this is K, which is contained in V. Set of vertices, and I can check whether H is colored red or blue is colored or K is colored blue in polynomial time. So this is my verifier. Okay, and it also takes the graph G. Input is G, H, K to the verifier. V of G, H, K, and therefore the problem Ramsey is in pi 2. Why pi 2? Because there is for all first, then there exists. Getting it? And that's it. Yeah. So, okay, we've come to the end of the session. I could not, I'm sorry I could not discuss too many questions, but we did a more in-depth analysis. Is there a Discord Slack channel of the subject? Can we get 2 sessions of the subject per week similar to other subjects, even 3? No, currently NPTEL scheme, PMI scheme does not allow 2 per week. It's only once per week for this particular course at least. And because the other subjects, Goel, the other subjects are actually, there are more people. So that's why they are actually having 2 or 3 problem solving sessions. Rosalind says, can we do weekends? Oh, sorry, Rosalind, this is already fixed, and there are specific instructions that this cannot be changed. The once the slot is fixed, then this cannot be changed. So weekends, yeah, it's not possible. I'm really sorry. Another question is, Goel says, is there a Discord or Slack channel in subject? Okay, so oh, is it recorded and uploaded then? Yeah, it is recorded and uploaded to my YouTube channel. Okay, and